In this section of the chapter notes, I want to talk about measures of relative standing. Measures of relative standing are numbers that we use to decide whether, relatively speaking, two data values are extremely different from each other or extremely different from the mean. So just to mention what those different measures are, one is the z-score, which we've worked with a little bit in a previous chapter. The second is the percentile or percentile ranking. You may be familiar with this just from your regular life. Closely related to percentiles are quartiles. Basically, what percentiles and quartiles do is they take your data, which you can imagine is distributed along a line, just like the real axis, the X number line or whatever, and there's your maximum value and there's your minimum value. So for percentiles, you would take that pile of data and that segment there and divide it up into 100 equal pieces, and each of those pieces would be a percentile ranking. And so if you divide this up into 100 equal pieces, each one would be a tenth or 10%. So you would have the 10th percentile and the 20th percentile and the 30th and so on to the 90th percentile. And so you have these percentile rankings, and the percentile ranking essentially tells you what percent of the data your score is better than. So for example, if your percentile ranking puts you here in the data scale, then your percentile, say your percentile ranking is that you're in the 80th percentile, that would be 80p, and then we would say that your score is better than those 80% scores. You're higher than 80% of the scores. Quartiles are similar, they just take the data and divide it up into 4 equal pieces, just like that. So there are actually 3 quartiles. This would correspond to quartile 1, which is abbreviated Q1. This position would be quartile 2, which is, again, since it's right in the middle, that would be the median, and that median would also correspond to the 50th percentile, because 50% of the data is above the median and 50% of the data is below. And then finally, that would be quartile 3. Q3 is the score that has 75% of the data below it. We'll see more about that in a bit. And then finally, more details about box plots. So recall the empirical rule for data with a bell-shaped distribution. It's very important in this section that you make sure you understand that rule, the empirical rule, and it just marks off the data values on a scale that is equal to a standard deviation. So we start with the mean at the center of the distribution. Now, if you recall, on the real number line, our starting place is 0. Then we mark off a length that's equal to a single standard deviation, and we mark that with the mean plus 1 standard deviation. On the real number line, that would correspond to the real number 1. And if we go 2 standard deviations above the mean, that would be the mean plus 2 standard deviations. On the real number line, that would just be where we'd mark the number 2. So on the real number line, the choice of your unit is sort of arbitrary, but in statistics, your unit is a standard deviation. So however long a standard deviation is, that's what your unit is on the horizontal axis. And that's all we mean by a standard deviation. And it tells us how, because we use the standard deviation as our unit of measure, we can talk about how far away from the mean a score is by the number of standard deviations. And so if a data value is 1 standard deviation from the mean, we associate it with the number 1. And if it's 2 standard deviations away, we associate that with the number 2. And remember, these numbers are called z-scores. Z-scores don't have to be whole numbers, and we'll find out about z-scores. Well, we've already used z-scores that aren't whole numbers. But it basically comes from that empirical rule. So how can we use z-scores to talk about relative standing? So I have this little example of LeBron James, who is a basketball player, and Taj McWilliams Franklin, who plays for the Minnesota Lynx. Now, LeBron James is obviously absolutely taller than Taj McWilliams Franklin. He is 6'8" and she is 6'4". So actually, he is actually taller, but in a relative sense, relative to how extreme their height is, who is more relatively tall? Who is further away from the mean height for their population? Well, the population that LeBron James comes from would be the males, and so if we look at the mean height of men, we see that that's 69 inches. The standard deviation of men's heights is, that's a population value, so that we're using the Greek letter sigma, 2.8 inches. Now, we look at the population for Taj McWilliams Franklin, and that would be the women, and so the mean height of women is 63.6 inches, and again, that's a population value, so we're using the Greek letter to indicate that, not x bar, but mu. And the standard deviation of women's heights is sigma equal to 2.5. Now, we have this information, and we know that LeBron James is taller than Taj McWilliams Franklin, so we know that if the mean is here, if the mean is located in this position, we know that we'll have to go to the right to locate both LeBron James and Taj McWilliams Franklin, but we don't know anything about the standard deviation enough, or we don't know enough yet to show exactly how much further away from his mean LeBron James is from than Taj is from her mean. So let's see what I mean. First of all, we have to decide whether the weights and heights in a population are normally distributed. And in fact, heights and weights are normally distributed, approximately normally distributed in any population. If you think about it, there are very few people who are very, very tall or very, very small, short. And most people have approximately average height. So heights are normally distributed. Therefore, the empirical rule does apply with height and weight data. And we're using data here. So let's calculate LeBron's heights distance from the mean of men heights. So to do that, we take the score x and subtract the mean and divide by the standard deviation. And in this case, the mean is a population mean and the standard deviation is a population standard deviation. These are the numbers. You can get those again from the previous slide, and you end up with 3.93. So that means that LeBron James is unusually tall because his height is more than 2 standard deviations above the mean. It's almost 4 standard deviations above the mean. His z-score is 3.93. You can do the same calculations for Taj's height and calculate her z-score in the same way, and you would get 4.96. And you see right away that Taj, relatively speaking, is more extremely tall than LeBron James is, because she's almost 5 standard deviations away from the mean height for women, whereas LeBron James, he's still very tall. He's very unusually tall, but not as unusual, if you will, as Taj. So if we were to arrange, now that we know our scale for our standard deviation, if we were to arrange, and also we can put them both on the same scale because it's just a standard deviation. So we know how many standard deviations above his mean LeBron James is. That places him on this position in extremeness. And Taj, her z-score places her in that position in terms of its extremeness. And we can see that Taj is more extremely tall than LeBron James. So in a sense, she's taller than he is. Well, the other nice thing about this is that you can use z-scores to compare extremeness even for measurements that measure different things. In the previous example, both of our original measures were measures of height. But here we can use the z-score to compare the height to the weight of an individual and decide which of those is a more extreme value. So if you look at the height of, I don't remember where it's this data right here. So read that problem and then look at the calculations right here. If you look at the z-score for a height of 76.2 inches, it's 2.6. So that's extreme because it's more than 2. If you look at the z-score for a weight of 237.1 pounds, that's 2.45. So it's still an extreme value. It's in the tail. It's more than 2. But which one is more extreme? The height is more extreme. So this person is unusually tall and unusually heavy, but the height is more extreme than the weight. Now, this all comes from the range rule of thumb, and it's all related. Just remember, the range rule of thumb says that extreme, rare, or unusual values are any values that are more than 2 standard deviations from the mean in any direction, either direction. Now, we spend a lot of time using normal distributions here in this course, so it sort of gives you that impression that all data is distributed normally. But this is not necessarily the case. However, in these examples, we're mostly focusing on normally distributed data. So we get this nice result that ordinary values are within 2 standard deviations. So you see the z-score is between -2 and +2. Unusual values are further away than 2 standard deviations. So the z-score would be less than -2 because -2 is here. The number is less than -2 or that way. Or greater than +2. So +2 would be here, and the numbers greater than +2 would be there. So these z-scores would be z-scores for unusual data values, so whatever you're measuring. And these would be considered about average. Just remember that the z-score can actually be any real number. It doesn't have to be a 2 or a 3. And not only that, even though it's rare to get a z-score greater than 3 or less than -3, it can still happen. So it's very unusual to observe data that is that far away from the mean, but there's always some probability that's positive that you will find a data value that far out. It doesn't mean you will, it just means there's some probability that you will. So this line right here never crosses the horizontal axis. It never dips below the horizontal axis. So there's always room for data between the axis and the tail. So again, we have this data value of 237.1 pounds corresponding to a z-score that we calculated for this example, and we can see that it's more than 2 standard deviations above the mean when we locate it on the axis. So one more time, you want to remember in terms of the range rule of thumb, which is illustrated by this strip right here. This is our illustration of the range rule of thumb. If a data value is less than the mean, then its corresponding z-score will be negative. And if a data value is greater than the mean, its corresponding z-score will be positive. It's a little handy thing to remember when working with z-scores.